7.7. This is a fun section. I like this section. The title of it is what's called complex numbers. I don't know if you've seen this before in an algebra class or not. I don't make any assumptions. I'm going to start you right from the ground floor. We've seen the word complex before, and I know it's scary whenever we hear something's complex. Remember, complex in math is simply talking about structure. Okay, when we talked about complex fractions, it meant I had little fractions inside of a bigger fraction. Complex numbers just are going to mean that we have numbers that are two-dimensional. It's not going to be too big of a deal. You have all the skills to work with complex numbers. I just need to tell you what they are. So the first thing is, just to give you the context here, sometime in the past, I don't know who did this or when. I should really, if I was a good professor, I would look this up. But somebody asked the question, okay, can we solve this equation? X squared plus 1 equals 0. Now, if this was, you don't need to write this part down. If this was x squared minus 1 equals 0, well, we solved this. We actually did this problem way back in chapter 5. We would factor or unfoil the x squared minus 1, and we'd set the two factors equal to 0, and we'd have a great time doing it. But we know, if you remember your factoring, which would be good because there's a final exam, we can't factor a sum of squares. So whoever went on this little rabbit trail said, okay, since I can't factor this, let's say I bring the 1 over to the other side. So I'm gonna subtract 1 from both sides. So then I end up with this statement, which is a little confounding, that x squared equals -1. And so for your whole arithmetic life, every arithmetic teacher has told you when you square something, you always get a positive. You never get a negative, right? If you square -5 times -5, that's a positive 25. So, okay, we've got something that we have been told in the past is impossible. So at this point then, this is where we get our definition. Okay, we are going to say, okay, well, let's pretend. Let's suppose that we can solve this. What would the solution be? And so here's my definition. This is the new bit of information for this section, and then we're going to spend the rest of the section learning how to work with this definition. This definition is of what's called the imaginary unit. And this is what we define the imaginary unit to be. The imaginary unit is the number that will solve this equation. It's a definition. It's made up. So the imaginary unit is this. It's I for imaginary. I is equal to the square root of -1. Now, if you remember when we did the first section in this chapter, I told you when we have a negative under the radical, we write not defined. Well, now we're defining it. Okay, so now we're going to learn what to do mathematically when that happens. The corollary to this definition is that when I square this, I squared is equal to -1. So this right here, this is the only new information in the section. And it's big. This is a big deal mathematically. If you're going to go forward in math, if you're going to take trigonometry, if you're heading to calculus because your major requires that, then you are going to encounter the imaginary unit a lot. In fact, my daughter she's studying engineering, and the particular part of engineering, this has lots of practical applications in things like waves and sending signals and things like that. So for something that's called imaginary and is kind of a made-up thing, it has a lot of real-world applications. So you potentially could see that quite a bit, the imaginary unit. So what we're going to do is we're just going to start at the beginning. Again, I'm not assuming you've ever done this before, so don't worry. So here's my first example. We're just going to practice. We're just going to practice simplifying when things that involve the imaginary unit, so we can get used to doing this. So here's my first example. Let's say that I have the square root of -25. In fact, this was a problem from section 7.1. And back in section 7.1, I said, well, we're just going to say that's not defined because it wasn't at that point, but it is now. So here's what you do. It's just the product rule of radicals, which we've done a bunch of. I'm going to take the square root of negative 25 and I'm going to separate it into negative 1 times 25. Well, product rule of radicals says I can consider each of these things separately. Let's do the part we know first. What's the square root of 25? 5. Great, we're comfortable with that. Now here's the new part. And I'm going to ask you this question a bunch so we get used to it. What's the square root of negative 1? The square root of negative 1 is defined to be I. So anytime you see a square root of negative 1, you are then going to write I. So the answer to this is 5I. This part right here is just the definition. Square root of negative 1, anytime you see it, is I. Here's one for you. I want you to simplify this. What is the square root of negative 81? Again, my hope is we do enough of these examples that you begin to, every time you see that negative, you're thinking imaginary unit, and you don't necessarily have to write this next step down unless you feel like you need to, which then go ahead. So first thing I'm going to do is I'm going to apply the product rule of radicals here. I see negative 81, so I'm going to break it up into negative 1 times 81. The 81, we've seen this before. The square root of 81 is 9. And then what's the square root of negative 1? What's that? I. Thank you for humoring me. I'm going to ask you that again and again. Okay, so we get 9 times the imaginary unit, or 9I. Let me just mention something before I end up erasing these. So if I is defined to be the imaginary unit, whenever you have something times I, like 5 times I or 9 times I, or on my next couple of examples, what these are called imaginary numbers. Imaginary numbers are something times I. Here's my next example. Next example is going to be this. Let's say I want to simplify the square root of negative 20. Again, we're going back through these negatives now, and we're doing stuff we've already done with our radicals. So here goes. First, I see the negative. When I got that negative under the radical, I'm going to write a negative 1 times. And now 20, we've done this problem before, but we're now doing it in this new context. What's the perfect square factor of 20? It's 4. 4 times 5. Our goal is always to find a perfect square factor. Okay? Well, now let's product rule of radicals. The product rule of radicals says I can consider each of these three things separately. So let's just go one by one. First, what's the square root of negative 1? That's I. What's the square root of 4? 2. Now, this is the normal convention. You have a little liberty here. Whenever you have a whole number, you tend to write your whole number in front of the I, like this is a variable, like you've always done. I can't do anything with the square root of 5, and so when we're writing things down, the normal thing is we write the square roots afterward. Okay, you don't have to. If you write the I as the last thing, that is totally fine. It's correct. Okay, but the reason this is done is if you write the I afterward, but then you accidentally write it under the radical, now you've got the square root of I, and that's a whole nother can of worms. So we're just trying to make sure our notation is clear. So I don't ever write the I after, because I'm a messy writer. I'm sure you've noticed over the course of the semester. So this imaginary number is 2I squared of 5. You okay? We're going to get used to it. I know this is a funky thing, so I get it. Let's try this one. This one's yours. I would like you to please simplify the square root of negative 54. All right, negative 54. I've got a negative 1. I see that part. Now the 54. What's the perfect square factor of 54? It's 9. It's 9 times 6. Remember, just take your calculator, go down that list of perfect squares until you find the one that works. So now, product rule of radicals. Product rule of radicals says I can consider each of these three things as separate radicals. So the square root of negative 1, that is our definition. That is I every time. The square root of 9 just becomes 3. And then the square root of 6, I can't simplify that anymore, so it stays square root of 6. Are we doing all right? Let me know, please. Speak up if you need me. Okay, so one more of these, just to show that even if the number can't necessarily be simplified, you can always take care of that negative. So go ahead and simplify the square root of negative 7. So the only thing that has to be done on this is I can't do anything with the 7. 7's a prime number. It's 1 times 7. But the negative, we don't leave negatives under the radical, even though we have this beautiful new definition. So what we're going to do is we're just one little step. Negative 7 is negative 1 times 7. Product rule of radicals says the square root of the negative 1, that is I, and then the square root of 7 is just going to stay square root of 7. So we always rewrite our radicals with the imaginary unit rather than the negative. So that applies to my next problem. I'm going to keep going unless somebody's got a question, so please speak up. You're doing your friends and neighbors a favor if you have the bravery to ask whatever question is on your mind. So here's my next problem. So I have the square root of 5, excuse me, not square root of 5, pardon me. Square root of negative 5 times the square root of negative 6. And I want to perform this multiplication. Now, I know what you want to do, and it's what I would want to do, but unfortunately, it's what we can't do. We can't just say, oh, cool, product rule of radicals, negative 5 times negative 6 is 30, and I got the square root of 30. Okay? We have to do one thing first. Before I can multiply, I have to write these in terms of the imaginary unit, just like we did on that problem there. So what I'm going to do, I'm going to write out the step here because I don't want to lose anybody. Negative 5 is negative 1 times 5. Negative 6 is negative 1 times 6. So the square root of negative 5 is I squared of 5. By the way, I'm hoping at some point we do enough that you can just go from here to here. That's my goal for you. Okay, I'm going to keep writing this step, but if you can just go, you see that negative and say that's I, that's great. You don't have to write this down at some point. And then here, square root of negative 1 is I times the square root of 6. So now they both have an I. They both have that imaginary unit. So if I asked you to hypothesize, I times I, what's I times I going to be? I squared. Okay. I squared. And then square root of 5, square root of 6, and square root of 30. One more step. So I times I is I squared. And I've got the square root of 30. The square root of 30 can't be simplified. There's no perfect square factor, but I can do one other thing. What is I squared defined to be? It's negative 1. I squared is defined to be negative 1. So this is negative 1 times the square root of 30, or just negative square root of 30. So I squared, this is my definition, that I squared equals negative 1. Okay, they're the same thing. And that's how we got that. You tracking with me? Did I lose anybody there? Well, if you change your mind on that, let me know. Do this one for me, please. Let's say that you have the square root of negative 4 times the square root of negative 49. Multiply those two things together. And so here's the step I'm going to write, and if you don't have to, that's good. So -4 is -1 times 4. -49 is -1 times 49. Product rule of radicals says this square root of -1 is I, the square root of 4 is 2I, square root of -1 is I, square root of 49 is 7I. So this time, the only difference between this problem and my previous example is this time the radicals worked out. And so now 2 times 7 is 14. I times I is I squared. And then humor me on this. What is I squared equal to? What's that defined to be? -1. So what this is really is 14 times -1, and that is -14. Again, because of the definition. Here's one more of these. It gives you a chance to practice writing things in terms of the imaginary unit and then multiplying and practicing both aspects of the definition. And then after this, we're just going to talk about what a complex number is and the operations that you can do that we're going to talk about in this class with complex numbers. So one more of these, square root of -7 times the square root of -11. All right, so I've just done the first step. Each of these has a negative under the radical. So the square root of -7, I wrote as the square root of -1 times 7. The square root of -11 is the square root of -1 times 11. Now I'll use this opportunity to write these both in terms of the imaginary unit. So the square root of -1 here is I square root of 7. The square root of -1 here is I square root of 11. I times I is once again I squared. Square root of 7, square root of 11 is square root of 77, which will not simplify. And then one final time, I squared is defined to be, thank you very much for participating, -1. So we have -1 times the square root, so that's just negative square root of 77. That's just the definition. All right, so that is what the imaginary unit is. That is that is how we devise imaginary numbers. So the title of this section is complex number. Here's what a complex number is. Okay, a complex number is any number that can be written in the following format. Okay, as A plus B times I. It's a two-dimensional number. This part, the A, represents the real part of the number. The real part is just the number system like we've been using ever since we learned about numbers. And then the B times I, this is the imaginary part. So I'm just going to write down, just to make sure we're clear, I'm just going to write down a few complex numbers. So here are complex numbers that have both parts. So for instance, we could have 3 plus 5i or -2 plus 11i. We could have any numbers. We could have a half minus 5/4 I. It doesn't matter. There's no limitations. Each of these numbers has a real and imaginary part. They are complex numbers. Also, imaginary numbers are complex numbers that just have a 0 for the real part. So for instance, the numbers that we've been dealing with, I square root of 7, and then 11i and minus 3i. These are complex numbers that have a 0 as the real part, but that they're called imaginary numbers, but they are also complex numbers. Complex numbers is a big set that describes pretty much any number you can work with now. And also, all the real numbers we've ever worked with. So like 3/4, and then 12, and then -17. These are complex numbers that have a 0 for the imaginary part. Okay, so all the plain old real numbers, all the plain old imaginary numbers, you combine them together into one big pot, and you get your complex numbers. Okay, that's what those are. So we are just going to talk for the last few minutes of this section about 3 operations on complex numbers. We're just going to talk here about adding and subtracting and multiplying. When we revisit these in college algebra, we'll add to it powers and we'll add to it dividing complex numbers. Okay, but right now we're just going to add and subtract and multiply. So here we go. Let's add some complex numbers. You know everything you need to know, by the way. There's no new information here. Okay, the only new information today has been the definition of the imaginary unit. So to add complex numbers, here is my example. So let's say I have 8 minus 3i. That is my first complex number. Now I want to add to it -2 plus 14i. So my first complex number is 8 minus 3i. The second one is -2 plus 14i. Well, if you did not know that I was the imaginary unit and I was just a variable you thought, what would you do to this to simplify it? Not going to FOIL, this is adding, but hold on to that thought, because when we multiply, that's what we're going to do. When we add things, what do we add? The like terms, the common terms. Yes, exactly right. So it's just adding like terms, just like if it was a variable. So we're going to add the real parts, we're going to add the imaginary parts, then we're done. So the real parts, 8 plus -2, you pop that into your calculator. 8 plus -2 is 6. That's my real part. Then the imaginary part, -3i plus 14i. -3 plus 14 is plus 11i. We're done. There's my complex number answer. So the reason they're called complex numbers is not because they're super complicated to deal with, but because there's 2 dimensions to them. Here is an addition problem for you. Please add -11 plus 17i. And to that, I would like you to add 14 minus 12i. So adding the real parts, adding the imaginary parts, here's what we get. The real parts are -11 plus 14. So -11 plus 14 is 3. And then 17i plus -12i, 17 plus -12 is plus 5i. Anybody get something different that we got to talk about? Just adding our like terms. That's all we're doing here. So that's how you add complex numbers. I don't have any more to say about that. It's adding like terms. The next thing we're going to do is we're going to subtract our complex numbers. So I'm going to take my previous example and I'm just going to change it from an addition problem to a subtraction problem. So 8 minus 3i. Now this time I'm going to subtract -2 plus 14i. I'll give you a moment to write that down. Now, if you and I had been together way back when you first had introductory algebra, what I would have told you, and what I'm hoping your teacher told you, is whenever you're subtracting polynomials, so that you avoid any sort of mistake, I would distribute the negative. So I would take this negative and I would distribute it. That way I don't have any sign mistakes and I get the right answer. So my first step here is I'm going to distribute that negative, then I'm going to collect the like terms. So my first number, the 8 minus 3i, does not change. And now I'm going to distribute the negative. A negative times a -2. Negative times negative is +2. A negative times a +14. A negative times a positive is -14i. And now I can collect my like terms. The real part to this, 8 plus 2. 8 plus 2 is 10. The imaginary part, -3i minus 14i is -17i. And there we go, we're done. Here's a subtraction for you. -12 plus 3i, now you're going to subtract 8 minus 5i. And once again, I'm going to distribute that negative. So this is going to be equal to -12 plus 3i. I don't change that first complex number at all. Now I'm going to distribute a negative times 8 is -8. A negative times negative, a negative times negative is +5i. And so hopefully what we're all looking at, and if you get something different, let me know. -12 and -8 is -20. 3 and 5 is 8i. I got one more problem. This one's going to have both an adding and a subtracting in, just to make sure that you're comfortable doing both. And then we'll finish off this section talking about multiplication. So here's your last problem of adding and subtracting. 14 plus 7i plus 2 minus 9i, and then minus 3 plus 7i. All right, so what I'm going to do first, there's a couple options on what you want to do. What I'm going to do first is, the only thing I'm going to do is I'm going to distribute that minus sign, and then I'm going to come back through the second step and collect all my like terms. If you wanted to do the adding and then distribute, if you want to do the whole thing in one step, it's great. Okay, there's other options here. So I've got 14 plus 7i, that's my first. It's my first complex number. I've got 2 minus 9i, that's my second complex number. I'm going to distribute a negative times a positive 3 is -3. A negative times a positive 7i is -7i. And now I'm just going to collect those like terms. I'm going to add all my real parts, add all my imaginary parts. 14 and 2 is 16. 16 minus 3 is 13. 7i minus 9i is -2i. And then that -2 minus 7 more is -9i. Just a couple more problems from this section. We are almost good to go. We talked about adding, collecting like terms. Subtracting is also just collecting like terms. So the last operation is to multiply. Again, you've done all this in other contexts. There's nothing different here for this problem as opposed to anything else you've ever done in algebra. The only thing you got to remember is what that definition is. So here's my example. Then I've got 3 for you to do. So I've got 5i times 6 minus 4i. So I've got an imaginary number times a complex number. So imaginary number times a complex number. So when you're looking at this and we want to get rid of the parentheses, what am I going to do with the 5i? What's that called? I'm going to distribute. Yeah, you've done this 100,000 times. Okay, so I'm going to take the 5i times the 6, and 5i times 6 is 30i. And then I'm going to take the 5i times the negative 4i. 5 times negative 4 is negative 20, and I times I is I squared. If you got that, you successfully distributed, you've done a great job. But now we've got one little thing to consider here. These are not variables. This is the imaginary unit. What is I squared? So this is negative 1. So this last term right here is negative 20 times I squared, meaning negative 20 times negative 1. So what is that? Positive 20, yes. Don't forget that. And now when I write my answer, now if you write this as 30i plus 20, I will not mark it wrong. It's totally good. But the good habit to be in, the normal convention is to write the real part first. So I'm going to switch it up and I'm going to put the 20 first and then plus 30i. So here's a distributing problem for you. Try this. Negative 3i times negative 6 plus 12i. All right, check your numbers with my numbers. Whatever questions you have, let me know. So a negative 3i times a negative 6, a negative times a negative is a positive 18i. And then a negative 3i times a positive 12. Negative 3 times positive 12 is negative 36. I times I is I squared. Again, the definition is that I squared is negative 1. So since I squared is negative 1, what is this last term? It is positive 36. Okay? A negative 36 times a negative 1 makes a positive 36. And so here's my answer. I've got 36 plus 18i. A question about where either of these numbers came from. All right, second to last problem. You're going to do this. This was already on your mind earlier for a different problem. So 2 minus 3i times 4 plus 7i. We're multiplying. So that, again, like we started off doing today with our radicals, it's just a foiling problem. Do your first outers, inners, lasts. Don't forget the definition, and you'll get to the finish line. First, outers, inners, last. Again, let me know if you get something different. I want to talk about it, make sure we leave here pretty clear on doing this. So my firsts, 2 times 4 gives me 8. My outers, 2 times 7i, should have had 14i. My inners, negative 3i times 4 is negative 12i. And then my lasts, negative 3i times 7i, negative 3 times positive 7 is negative 21. I times I is I squared. We okay? Anybody got something different? Okay, 2 things I'm going to do simultaneously here, if you will allow me. The negative 21i squared, what is that really? It's plus 21. Reason? I squared is defined to be negative 1. So you just make that substitution. Negative 21 times negative 1 is positive 21. Now I'm going to add 8 and 21 is 29. 14i minus 12i is plus 2i. Last problem for this section is just another multiplying, just to make sure we feel pretty good about it. And then we are going to finish up our semester of material. It's a very exciting day. 7 plus 2i times negative 3 minus 2i. All right, here goes. First, outers, inners, lasts. So my first, 7 times negative 3 is negative 21. Outers, 7 times negative 2i is negative 14i. My inners, 2i times negative 3 is negative 6i. And finally, 2i times negative 2i, a positive times a negative is negative 4. I times I is I squared. You should have those 4 terms, doesn't matter what order you have them in, and now we'll collect the like ones. Before we do that, one more time, negative 4i squared turns out to be plus 4, because this is negative 4 times negative 1, that's what that's defined to be. And so negative 21 plus 4 is negative 17, negative 14 and negative 6 is negative 29. There's my end result.